Hi, Guy Moxey from Wolfspeed Power, and we love the first episode so much we decided to do another one. So join me for a further conversation with Alex Lido from EPC. You mentioned one thing, X-ray, very radiation immune, and I know you've got something right next to there that I'm fascinated to see.
One of my coolest applications, I have to say. I'll show it here. There's a pill, and everyone looks at it and says, "I don't want to swallow that pill," and I say, "Well, you do, because the alternative is worse."
Right.
This is a colonoscopy pill.
Okay.
It's approved in Europe. It's coming in the U.S. maybe in a year or so, and inside of it, there's an X-ray machine. It's a tiny little X-ray machine.
Right.
It's GaN runs the motor and the power supplies and all that kind of stuff, and it uses a small pellet of irradiated metal, and this thing rotates and takes an X-ray of your colon as it goes through.
Okay.
You don't have to purge ahead of time, which is, anybody who's had a colonoscopy know that's one of the two bad things. I also got asked this just yesterday, and is it recyclable? No. So that's the third problem that's eliminated there. This is made possible because of GaN. But it takes a high-resolution image of your colon, and it sends it wirelessly to a patch that you wear on your back.
Oh, so it transmits. It doesn't store. It transmits out.
Transmits. If it stored it, it would have to be recovered.
Good. No, that's one of the third things. Yes. Okay. Understand.
Right. So, and this is now, as I said, this is coming to all of us soon, and all of us over 50 remember this because it's the best alternative I can think of.
That's just astounding. It's just absolutely astounding of what a power semiconductor can do. Oops. You've also got another example here of power density, which is power densities are a big thing for silicon carbide, making big things a lot smaller. Our big things are huge, but please let's have a look at some of the stuff you have.
So this is a first high volume DC to DC converter that went into high density servers. It's from MPS.
So it's silicon
monolithic power system. No, it uses our GaN.
Okay.
Uses a lot of their stuff, and then our GaN.
Right.
And it's 300 watts, and this is sold in the very high volume right now today. But servers and AI machines are becoming more and more power intensive. So now they're moving to a kilowatt system. So this is 300 watts. This is a kilowatt system. Uses about 4 times as much as our GaN to get to a kilowatt. Okay, it's still maybe about 3 times the size of it. So that's good. But this is now getting big. So what we had to do was, with our next generation of GaN, is we shrunk the kilowatt one down to that size.
Okay.
So this kilowatt device with new generation of GaN that's been out about a year is now smaller than that 300 watt from 2 years ago.
Yeah, the original one. Yes.
Yeah.
And that's a 2-year design circle of learning.
About a 2-year cycle of learning, exactly.
Okay.
And we're just beginning. We have another factor of 2 coming. We have more factors of 2 after that.
Okay, so how do you deal with power densities coming down, chip sizes are getting minuscule, amps are going up? How do you deal with the power dissipation? Because that's our biggest headache. It's been a silicon headache for decades, hasn't it, as die sizes get smaller. How are you tackling that in EPC and the lower voltage side of wide bandgap?
Yes, so a couple of years ago, one of our customers said, I love to use your GaN, but I just can't because it just doesn't pencil out thermally.
Yes.
We can't get the heat out. And so that started us on a real deep thinking project on, why is that? And we found out that people's intuition about thermals is actually wrong when it comes to GaN, particularly the way we make GaN, which is chip scale.
Okay.
So it doesn't have a package around
it.
Right. And because it doesn't have a package, it's a little bit like on a hot day if you go out in a bathing suit compared to going out in a heavy black coat. Most power devices are like a heavy black coat. They hold the heat in far more than we understood. And so by getting rid of that, we were able to get the heat out very efficiently. And not only that, but we don't dissipate as much heat because GaN is a more efficient power converter.
Yes.
So first don't generate it and then get it out much more efficiently.
Yeah.
Then we took it to the next level. We said, well, getting it out efficiently means you have to go through other things like thermal insulating materials and heat sinks. And so we did work with vendors of those things and improve those materials. And so now a thermal insulating material of about 2 years ago was the best you could get would be 6 watt per meter Kelvin. Now you can get them at 18 watt per meter Kelvin, and we've even developed devices that, because of their topology, can take away the insulating requirements, and you can get 40, 50 watt per meter Kelvin out of it, which means you just suck the heat right out of it.
Brilliant. I mean, are you looking at sort of embedded into PCBs, and what's next on the thermal side? You've been doing chips. You started with chip scale right out the chute, didn't you?
Yeah.
So what are you seeing next? Because it's a challenge that we get faced with, and we're looking at different interface materials. It's a little bit different for us because we're blocking 600 to 3.3 kV volts. So they've got a lot of creepage and clearance. You have a slightly different perspective. But what do you think's next on the thermal side of things?
Well, I think that on the thermal side, we've actually developed packaged parts that are almost as efficient as chip scale parts. So they're a little bit easier to handle and pair all together in large quantities. In terms of embedding it into a PCB, a lot of talk around that.
There is,
but I see that as a thermally constraining approach.
Yes, you're putting a jacket back on.
Yeah, you're putting a jacket back on. Now, if you clad it on both sides with copper and put a heat sink on it, maybe that's okay. But now you've made your PCB much more expensive.
Yeah, it becomes more exotic, and exotic means less commercially as acceptable. So, there's always barriers to entry in any technology. I think both in silicon carbide and in GaN, we've knocked down, between us and the other players in the industry in different ways, we're continually knocking down these barriers, and the adoption is there. But one thing you and I have spoken about in the past as well is long-term ruggedness and reliability.
Yeah.
You were having the same conversations to a different audience, but as I was 8 years ago, what is it? 5 years ago, we know what it is, how do we use it? Now it's more so, right, we're using it, but is it going to be around in 5 years, 10 years? What's the long-term reliability? Because qualification is not long-term reliability. Right. So, there is, again, pros and cons in all technologies, but wide bandgap in general is a rugged technology. So what sort of typical frequently asked questions are you getting in the GaN side of life?
So, people are generally risk averse, and so they don't want to try new technology unless it's been truly tried and tested. And not only that, it's easy to bubble up fear. I remember in the early MOSFET days, Motorola, which was a big bipolar transistor one, they used to kind of throw around, it's got that very thin oxide in the gate. Yeah. You got to watch out for that. It's not going to be very rugged. Because they really didn't want a MOSFET. Well, today we have a lot of the traditional MOSFET people also throwing out that kind of insinuations, most of which aren't true, but many of them are just insinuations.
Yes.
So early on, because of the MOSFET experience, I realized that we had to really understand the reliability. And we went into a test to fail philosophy from the very beginning, where you don't just qualify a device by testing it and, say 100 parts for 1,000 hours, no fail, oh good, I've qualified.
Tick the box and off you go.
All you know is that it didn't fail for 1,000 hours at that temperature and condition.
Yeah.
You don't know how it would behave in any other condition. So we started taking devices and massively failing them, and then figuring out exactly what are the conditions under which they failed, propping up that part of the device to make it stronger until it's stronger and stronger and stronger, and then that would be a launch product, and it would be incredibly rugged. And our devices are unbelievably rugged today, much more so than silicon. There's also a fundamental advantage. Wide bandgap devices, the wide bandgap is actually caused by a stronger chemical bond between the elements in the crystal.
Yeah.
What that means is it's a tougher crystal. And it is also less sensitive to temperature effects.
Yes.
So wide bandgap, silicon carbide, GaN, both have the same thing, is temperature is your friend as opposed to your enemy.
Yes, you're not running away from it, that's right.
No, at higher temperatures, it is demonstrably more reliable at 150 C than it is at room temperature.
Oh, yeah.
So, you get these completely different ways of thinking about reliability, and you have to educate people.
Yeah, and it's, down to the packaging, chip scale or epoxy for us and modules. And, You're right. 1,000 hours is a good release, and you qualify to the same standards as silicon. So do we. But that long-term rel, that bathtub curve, you come down, you're in that flat plateau bit for 20 years, and then, when do you start expecting to see those failures? And we're doing the same analysis. You and I have the luxury of running GaN or silicon carbide for 60 million hours to see when it will fail. So you have to push it to destruction. And we certainly, from our side of life, can confidently say that we are as rugged or more rugged than silicon, and you certainly can as well. And your field hours, we've been running for 15, 20 years, but our field hours now are clocking up nearly 8 trillion field hours, and our fit rates are single digits, and you're getting the sort of similar fit rates as well. So I don't think anyone should be afraid of long-term reliability. This is not, people say it's a new technology. It is in some context, but in other ways, it is not. Yeah. It's absolutely mature and it's prime time. Absolutely. Yeah. So we've talked about some of the applications, reliability from both sides of our fence. Where do you think over the next 10 to 20 years this is going to go? Let's talk about your 200 volts and below for a start off, Alex, if we can.
Yeah, look, I think that over the next 10 to 20 years, silicon is going to, again, go into zombie mode like bipolar transistors did many years ago. And the break point, we've got 650 volts and below for GaN, and above that for silicon carbide. For us, the road is filled with integrated circuits. Yeah. There is absolutely no reason why you don't put a driver onto a FET. It's hard to do in silicon, it's easy to do in GaN. So we're doing more and more of that. It adds performance and reduces system cost much faster than it adds component cost. So I'd say that starting in about 2024, it'll probably be that EPC doesn't introduce discrete devices anymore. Okay. They're all some form of integration. Now the integration will take a couple of forms, just simple drivers plus FETs, or systems in half-bridge complements. Yes. For example, a multi-level converter, an N-level converter, can actually be integrated onto one chip in GaN. And that's a very interesting topology for a lot of reasons, because you don't need high voltages. You can create high voltage out of low voltage devices. But also, monolithic half bridges. This is an example of a motor drive that goes on an electric bike. And it's just three ICs from us. Just three ICs and a controller, and the whole system's done. Yeah. So these are the kinds of things that this is multi-billion-dollar markets. Yes, right there. Absolutely.
And from our side, we're just starting to introduce what we call mid-voltage, so anything above 1700 volts, and that brings in a totally different landscape and dimension. Yeah. Scary stuff, and a lot to do with packaging. Not many people want 3.3 kV die. Some do. But a lot of it's around packaging. But again, there's some barriers to entry, but once you talk about reliability, if we're going into windmills and microgrids and grid distribution, then that's got to be up on poles for 20 years. So we've got to walk through step by step that reliability, but some incredible markets to exploit. Yeah. And silicon will be around for a while, but it's shown its limits in your side of the game and certainly in our side. So exciting times, Alex, for sure.
Oh yeah.
Now you mentioned a bit of an interesting topic here. You mentioned GaN going from 20 volts to 650. EPC stop at 200. And obviously when we get to 650, we're starting to get a potential crossover with silicon carbide. What was the decision for EPC to sort of stop at the 200 mark?
Yeah, actually we have 350 volt devices as well, but the bigger market's down at 100, 200 volts. But the reason was when I was at International Rectifier, I was the largest producer of MOSFETs and IGBTs in the world. So I saw the entire spectrum. Yeah. So now when you're going to a business with GaN, I thought back to all my experiences, and all the customers that I knew that were in the lower voltage range were begging us for smaller chips that were faster. And all of our customers at the 600 volt level were begging us for lower prices. So I said, okay, there is a clue.
Not much has changed, by the way.
And it has not changed. It has not changed. It is a fast commoditizing node at 650, whether it be fast chargers or AC inputs or whatever it is, everybody chases into it and it becomes a price war.
Yes, yeah, very, very quickly. That's true, that's true. But there are still players around looking at that market, and it is a large market driven around the consumer space.
Yeah.
And just comparing that to silicon, it absolutely makes sense. An integrated flyback, for example, switching at a megahertz, makes the power supply, as you show, power density comes right down. Right. So another example, even a more congested market, but another example where silicon has done a good job. It's done okay, a bit like my school report, done okay, could do better, but unfortunately can't. So exciting times. But one last thing before we sort of wrap up. You and I have been in this industry quite a while. We've seen a lot of trends, seen a lot of people come and go, and it's nice that power electronics is front and center and sexy, if it ever could be sexy, depends on perspective, which means a lot of new people are coming into this, which is much needed. People have got to be smart, kids, I'm not saying kids. Graduates have got to be smart to get into this game anyway, so there's no shortness of smarts. But if you had your sort of cycle again and you were coming out of grad school, and you were looking at the market it is today with the different technologies and the different end systems, what sort of things would you be saying if you were in front of a rotation program intake? Mm-hmm. What sort of things would you be saying to them today? Because it's a very different world now than it was.
Well, I think that when you're young, that's the time to take risks. You have less to lose, for one. Mm-hmm. And as time goes on, you have more obligations, you can take less risks. So that's the time to take risk and shoot ahead of the market. That's the risk that I would recommend that a new graduate take. Mm-hmm. And today, what's ahead of the market? In the world of digital, it's a little hard to identify what that is.
Yes.
In the world of power, it's pretty straightforward. It's wide bandgap stuff.
Yeah.
So we're seeing that people that are actually interested in electronics as opposed to software
mm-hmm.
Are really flocking to this.
Yeah.
And we have quite a big pool of people interested in getting into wide bandgap, and it's a lot of fun to do that.
It is, finally. There's some more life into it. There's some great schools doing some great programs, and you're right, when you're young, you can afford to take a risk, and if it doesn't quite work out, you can recover. I think you've got to be mobile. Mm-hmm. The world's a small place, whether it's Southern Cal, Northern Cal, automotive in Bavaria, or over in Asia on some of the renewable stuff. There's incredible opportunity if you're willing to be more mobile. You instigated and ran a very successful rotation program, IR. I was part of that, and I believe it was 2 years and 6 months placements all over the world.
Yeah.
Incredible opportunity. We're implementing that at Wolfspeed right now because we just need to bring on this new talent, and it's incredible to see. It really is.
Yeah, and at EPC, we're already starting to hire people with that in mind, that they will be rotating and becoming more familiar with various facets of our business.
Yeah, I think you're doing as much as EPC is still a startup, a very entrenched, well-known startup.
Startup means not profitable. We're 15 years old, but okay.
Soon to be. But thinking about I'm talking about GaN more so now than Silicon Carbide. Silicon Carbide's really a larger company game due to the sheer expense of doing it. But what's the angle around GaN for a smaller, leaner company compared to a larger, big semi company?
Yeah, I don't think GaN has been appropriate for large companies. Several of them have tried it. International Rectifier tried it, and Infineon's trying it, ST's trying it.
TI, some of the analog guys are, yeah.
Dialog, they all try it. But what they don't realize is, number one, is we're in the recycling business. GaN can be built in a standard silicon factory.
Of course,
so
yes.
we recycle old factories,
yes.
which are already fully depreciated.
Yeah.
Good news. It means a very low capital investment, which means you don't have to be a big company to afford to do it.
Yeah.
The second thing is it's a fast evolving technology. So you really have to, A, be willing to take risk, and B, fast cycle of learning. You really have to be urgent about each cycle of a new product or whatever.
Which a small, agile company is absolutely set up to do.
Right, exactly. Exactly.
Not saying that our friends in Munich are moving slow, but they are a big machine. TI is the same. It takes time and bureaucracy and teams to come together. And interesting you said about the recycling game. It's a new way of a new approach, because I haven't heard it said that. But you're right, there are plenty of 6-inch silicon fabs around, completely, well, maybe not empty at this second due to the market situation, but come 9 months' time, I think there are going to be a lot of empty 6-inch fabs. What about 8-inch?
Well, look, right now, every inch of fab is used everywhere over the world. We've been through that many times.
Yes.
And what's the flip side of that?
Oh, yeah.
There are a lot of 8-inch fabs available.
Yes, yeah, what comes up comes down.
We're already working in an 8-inch fab today. So,
fantastic. Okay.
So we're beginning to look at how to recycle that entire fab.
Brilliant. So the future for capacity. We talked about reliability, adoption, barriers to entry, capacity. You're in a better position with GaN than we are in silicon carbide. For us, it's really who's vertical right now and for the foreseeable future has the strength. But you're in a very different position. So interesting perspective, Alex, for sure.
Yeah.
So I won't take up any more of your time. It's been brilliant to have you here, and I know you've got to rehearse your GaN versus Silicon Smackdown webinar.
I do that every night.
Carry on doing it, because you've been a fantastic advocate for wide bandgap, and it's been such a great conversation, and we're going to carry on talking in conferences and various places going forward, and just really appreciate what you in the lower voltage side of wide bandgap are doing, because together there's that $20 billion silicon market that's out there that, needs a shake-up. Alex, thank you so much. You've been a fantastic addition to this episode of In the Studio. Great insight, and just pleasure to have you on. Thanks for being here.
Oh, thanks, guys. It's been a lot of fun.